today's topic is to take an overview of a relatively new indoor air quality standard, ISO 16000 parts 34 and 37. The agenda is fairly simple. We'll discuss a little bit on why these two standards are interesting as new standards, and we'll discuss the two standards themselves in detail, and we'll finish by looking at a few measurement setups that are compliant to this or these new standards. So first, to talk about the standard itself, this is an ISO technical committee standard from the technical committee 146 air quality and subcommittee 6 indoor air, and it's in two parts, part 34 and 37. The part 34 discusses sort of general strategies and guidelines how to measure indoor air quality in terms of particles. And then part 37 is specifically the standard method to measure PM2.5 mass concentration from indoor environments, and how also you can then use supplementary equipment to complement those reference PM2.5 mass measurements. So what's interesting about the ISO standards? By the way, if you are wondering, there are parts 34 and 37. So the ISO 16000 has, as you can see from the numbers, it has a wide range of different standards. The 34 and 37 are specific to particles, and then other parts of the ISO 16000 are like for formaldehydes or VOCs and other pollutants. So what's interesting here is that it has a well-defined reference method for PM2.5 in part 37 and a really wide range of supplementary methods which are discussed in part 34. So of course, going into the topic of indoor air particles, there are a very wide range of different sources for indoor air particles, and they vary depending on what sort of a room or what sort of a premise it is, like living room versus kitchen. And of course, there are differences in normal office environment to a kindergarten, for example. Typical sources for particles are one of the most common is cooking, of course. Then it's very much dependent on the quality of the ventilation system, on how much the cooking emissions affect the indoor air quality. Cleaning itself, especially vacuum cleaning, generates, depending on the quality of the filter in your vacuum cleaner, it generally generates quite high concentrations of small particles. Combustion, of course, whether it's candles, indoor fireplaces, or cigarette smoking, of course, generates quite high concentrations of particulates. One significant source may be heating appliances. Now we would be talking about electric heating appliances that are used intermittently. So when the heating appliance is not used, they usually gather some VOCs and possibly some grease, maybe from cooking or things like this. And then when it's heated up, they can generate really high concentrations of very small particles from the heating appliances. Then, of course, domestic animals and humans, our activity in general, are generating aerosols into indoor environments. Now, once the aerosol is generated in an indoor environment, it goes, of course, through continuous change. So there are the particulate sources that generate aerosols into an indoor space. There are particle sinks, like all surfaces. If particle comes into contact with the surface, it's removed from the atmosphere or from the indoor atmosphere. And this can be, for example, represented by the ratio of surface area to the total volume of any space. So of course, the more there is surface area, the more there are particle sinks. Air conditioning and ventilation type, and of course rate. It has a massive difference whether it's filtered or unfiltered ventilation. Of course, the ventilation rate is really important to reduce the concentration of indoor aerosol. This can of course also work in the other way if in case the outdoor concentration is very high and the ventilation is unfiltered, then of course ventilation can increase the PM concentration in an indoor area. And the particle size distributions change, of course, continuously as well due to aggregation and coagulation of the aerosol. This is typically fairly slow process, of course, because we don't normally have that high concentrations that the aggregation or coagulation would happen quickly, but it happens over time. Then, of course, as with the example of heating appliances, we could talk about secondary particle formation when you have volatiles leaving the heater and then forming particles through nucleation. So quite complex processes. As said, the standard method that will, or the reference method we'll discuss for PM2.5 is an gravimetric filter method, but the supplementary methods allow the use of real-time measurements. And this brings, of course, many benefits to the measurements itself. Of course, planning, when you're doing gravimetric collection, it's really beneficial to have some other, preferably real-time method to measure the particulate concentration as well, so you can estimate that you have collected a suitable amount of mass on the filter. And real-time measurements are critical in identifying particle sources. When you see that an appliance is used in an indoor dwelling, you can then, with a real-time measurement, easily check whether that whatever appliance it is generating PM into the indoor air. And related to this, specify the beginning and the end of particle release. Once again, coming back to the heating appliance, when you heat it up first time or after a period of time it has not been used, it generates quite a lot of particles, but then after it's heated up sufficiently, the particle generation usually decreases quite significantly. And with the real-time data, you can of course do temporal and spatial variation measurements in particle concentration, and very importantly, to compare the background concentration that should be measured before any activity in the indoor dwelling and versus the concentration of whatever phenomena is generating aerosol into the space. And one key aspect always, as we know with filter measurements, there are possibilities that there is just a problem in the filter measurement itself. For example, you might lose some of the filter material, or you might very simply do something that shakes some of the material on the filter loose, in which case, when you start to accumulate data with real-time methods and the filter mass measurements, you can then go back to the real-time data to check if your gravimetric result looks strange. You can check whether that result corresponds to the real-time data. And of course, I don't think you can get through any presentation nowadays without some reference to the ongoing pandemic. But especially this is important now, since we know that infection of COVID-19 via aerosols happens especially in indoor spaces. And ventilation is a critical factor in dilution of contaminants. And in this sense, once again, the real-time measurements are important since activity is critically important, whether it's a person who is not just sitting still and not talking or doing anything else, emits fairly low amounts of aerosols. But if there's talking, and especially if there's singing or shouting, that generates much higher concentrations. And of course, the real-time measurements allow studies on how to mitigate infection risks, meaning comparing situations when there are no precautions. Masks plus ventilation has a massive effect on the infection risk in any indoor space. So first, we'll take a look at the part 34, which is the general strategies for the measurement of airborne particles. Indoors has a long explanation in the standard. So we are talking about dwellings, which means any sort of a space where there are inhabitants. It's not a really clear cut, but basically any sort of living space, and also workspaces and public buildings. But these are only if they don't have some other industrial safety legislation already in place. So you are allowed to use this in offices, in shops and restaurants, schools, theaters, but you can't, of course, override any legislative measurements that might be required. In standards, there's always a scope of the standard, and in the scope of this standard, the only indoor spaces that are excluded where you can't use this standard is vehicles and public transportation, because there are separate standards for those measurements. So that's typical in standardization work. In any new standard, it's tries to be fairly carefully written so it doesn't overlap with any other standard where you might have then conflicting results. So it has the ISO 16000-34 has a very wide so there's scope on what can be measured. So particles from 1 nanometer all the way up to 100 micrometer, including PM10, PM2.5, and ultrafine particle fractions. The standard is very comprehensive. It describes general strategies for the measurements, methods for identifying typical sources. It has recommendations for obtaining representable samples, and how to determine measurement uncertainties, and what should be sort of the minimum requirements that you should do when you are doing indoor air quality measurements according to these standards. Quite a big part of the standard itself is discussing different measurement methods and their advantages and disadvantages. And as said before, recommendations how the real-time data can be used to get spatial and temporal information. The standard sets sort of base requirements, what you should always do when you are doing measurements according to this standard. Of course, good sampling practice should be used so to avoid losses, particle losses in any of your sampling lines. Measurement location, if any other consideration is not done, it should be at the center of the room. And if it's a really small place, like a closet, you can't take more than 10% of the room volume as sampling flow per hour. So there are that sort of limitations. There are requirements for the measurement time, duration, and time resolution. If you don't know the variation of concentration in any space, then you should select methods that have as fast time resolution as possible so that you're able to catch those events. Once again, you should have some sort of an estimation of the scale of concentration, because if we are talking about some very, very clean space, then there might be limitations on what instrumentation you can use. Then on the other hand, if you are talking about a space where there would potentially be very high concentrations, let's say a large kitchen with poor ventilation or a bakery or something like this, then you need an instrument with as wide as possible concentration measurement scale. You should take the background concentration into account. So what we mean by background concentration is that when you have an indoor space or an indoor dwelling, as said, you should measure the background concentration so that all the potential aerosol sources should be turned off, and there should be no like human activity in the room. Then it needs to allow the concentration to settle, which may take hours, but then to get a sort of background concentration baseline for the indoor space. The impact of outdoor air quality should be considered, meaning there should be simultaneous outdoor and indoor measurements, and the impact of room conditions. If there are changes in temperature, relative humidity, pressure, CO2 is a good marker for what is the ventilation rate versus how many people are there in a specific space. And then of course the impact of materials. So if depending on the whether the walls are painted or they have wallpaper, or what is if the floor is just let's say a stone floor or a wooden floor compared with wool rugs or something like that, that has can have a massive effect and should be noted in the measurement notes. And of course, the impact of the measurement itself should be minimized. We already talked about the maximum amount of sample you are allowed to pull from a room, but there are also other things like, of course, if the measurement instrument uses a pump, it's of course preferable that either the pump exhaust is very well filtered, or you use a dry or a scroll pump that doesn't generate aerosol itself. As a simple example. The other thing is, of course, the more psychological effects of the measurement. So whether the inhabitants of the dwelling behave in the same way when they know that they are being monitored, or the PM concentration should be is monitored. So if they behave in a different way, that of course has an effect also on the validity of the measurement results. Then the standard has so-called best practices. They've tried to write down what would be the sort of best recommended practices, which would then involve quite a lot of work, but this would be a very comprehensive measurement of the indoor air quality. So it would include preliminary work, of course, understanding what is the objective of the measurement and getting basic information of the like main expected sources. Is there smokers in the area? Is there a fireplace? What is the heating system like, and other things? And of course, trying to understand whether these are what is the temporal frequency of these sources, and of course what sort of an indoor area it is. If it's an office where people are working for 8 hours per day, it's probably reasonable to focus the measurements on those hours. And then a detailed description of the indoor space or the indoor compartment, as detailed as possible. Then to carry out a room inspection, indoor, as said, once again, properties, equipment, air tightness, which means how easily can outdoor air leak indoors, and if it's filtered in any way. And of course, the behavior of the habitants in the dwelling. For the outdoor, it should be noted, or at least there should be an attempt to look at what are the anthropogenic and the natural sources of PM. So to understand what sort of concentrations do we expect there for the outdoor surrounding PM. There should be preliminary measurements to make sure, for example, that your filter collection times are suitable. The preliminary measurements can be done with, let's say, more simple measurement devices if possible. So you don't need to do with it the full measurement setup, but rather you can do like identify sources in the preliminary measurements and do work like this to better plan the measurements themselves. Then for the measurement procedure, what should be done? We talked about the background measurement already. There should be also detailed notes on the outdoor influence, weather patterns, wind patterns, and of course the outdoor PM concentration. You should try to identify and evaluate the main sources in the dwelling, and then try to do efficiency measurements of abatement techniques. Like I personally, due to allergies, I have a fairly large air cleaning system in my house. So that would be, there would be measurements with that air cleaning system turned off and with that air cleaning system turned on to get an understanding of how efficient the abatement technique is. Then what is it not? It's not for biological particle measurements or biologically active particle measurements. There is a separate ISO standard for that. It's not for, as said already, not for particle measurements inside automotive cabins or public transportation. And of course, the standard itself doesn't set any limit values. So the limit values would come from legislation. So as said already, it has a wide range of different methods for the measurement of aerosols with many different measurements: particle number, particle mass, particle surface area, and the lung deposited surface area as examples. Different methods have different size and concentration ranges, as well as time resolutions. And the standard itself goes briefly through the operation principle of each method, advantages and disadvantages, and possibly related standards. So it's a fairly comprehensive standard. Now I could stop for a moment and see if there are any questions before we move on to the part 37. I don't see any open questions, and nothing in the chat either. Okay, we'll continue with the PM 2.5 mass concentration part of the indoor air standard. So this standard specifies measurement methods for indoor PM 2.5. It takes most of its text from EN 12341, which is the ambient PM 2.5 standard. There are limitations, not for concentrations below 2 micrograms per cubic meter, not for bioaerosol sampling, and not for chemical composition analysis of the samples. Of course, you are allowed to do those things from the collected filters, but you cannot say that you are doing this according to this standard because it's out of its scope. The reference method is fairly simple. So we have a gravimetric filter and a pre-separator, which is as defined in the EN 12341. In addition, it describes procedures for, as said, supplementary real-time measurements that help in understanding the data. So in terms of measurement strategy, general requirements, this is now a little bit repeating what's, of course, in the part 34. The basic requirements: center of the room, sampling point height about 1.5 meters, and there should be a minimum of one sample per room measured. And of course, the sampling point height would more or less represent a typical height of the breathing area of someone standing in the space. The indoor air conditions have to be measured, which temperature, pressure, and humidity. And it is highly recommended to do both outdoor PM2.5 measurements and CO2 measurements. The CO2, of course, as said, is representative of how many people are there in the dwelling and how well it is ventilated. So regarding the equipment, facilities, and procedures, the sampling system, the weighing facilities, and the weighing procedures are all directly as it's done in the EN 12341. So it's fairly straightforward in that sense. The differences to the EN 12341 standard is since we are not doing outdoor, the sample temperature conditioning is not always necessary, and the sampling period can be split within 3 days. So, as said, if it's an office building that has workers in there for the typical working hours, it probably makes sense to do the gravimetric sampling also, so that you split it into 3 8-hour periods. And very specifically, it is allowed for the purposes of the supplementary method to take a minor side flow after the inlet and before the filter holder to do the real-time measurement. So this is also not specifically banned in the EN 12341, but in this standard, it's stated that this is allowed to be done according to the ISO 16000. When we talk about the supplementary measurement methods, one important thing which is very different to the ambient side is that there is no equivalent method approval allowed for the indoor air measurements. So there is only the reference method and no equivalent methods. And the reason for this is that in indoor aerosol characteristics, there is much more variation compared to ambient measurements. Like, as we know, typically nowadays for ambient measurement stations, quite often nowadays in Europe, the measurements are done with optical systems, which have to be characterized against reference systems in long-term campaigns. And that equivalency can only be used in environments where you have similar aerosol to where you did those equivalency measurements. And this is not, or this is very difficult in indoor settings. So there is no equivalent method for the ISO 16000. It gives procedures for the parallel real-time measurements, how to supplement the gravimetrical results. There are some limitations how you're allowed to use it, but anyway, all of the methods that are allowed to be used are described in the part 34, the minimum size range of any supplementary method should be from 300 to 5,000 nanometers. It can be, of course, wider, but it needs to be at least this wide. You're not allowed to replace the gravimetric result with just a real-time measurement. And you cannot correlate the gravimetric measurement with the real-time data. But the real-time data can be used for quality assurance. It can be used for source and process determination. And what we already talked about, spatial mapping, time-resolved identification, and of course, it's very useful in determining a suitable collection time for the filter. Let me check quickly if there are any. I don't see any questions. So we'll crack on to the compliant measurement setups. Some examples of those. We have the LP Plus electrical low pressure impactor, which is compliant for a supplementary method, which gives you real-time size distribution and concentration, number concentration, mass concentration, and LDSA concentration and size distribution between 6 nanometers and 10 micrometers. It has a really wide dynamic range, so even from low background concentrations to situations where you have a high concentration source, you can measure it directly with the LP instrument. And with the use of the sintered plates as collection media, we have run the instrument for up to 6 months in uninterrupted measurements. So you can use it also in long-term measurements if needed. The setup is fairly simple. We typically would use an inlet, a PM10 inlet or a TSP inlet, a pump. Of course, scroll pump is preferred, and the pump can, in these measurements, place remotely and use a long vacuum line. So it's away from the instrument itself. And of course, the sintered plates as the collection media. I'll go through the operating principle just quickly. For the LP Plus, we have a vacuum pump that pulls the sample through our measurement column. And the sample first enters into a diode unipolar charger, where we have a thin needle that produces a discharge of ions. And the sample goes through this plume of ions and becomes positively charged. We have a small trap field here to collect excess ions, and the charged particles then enter into the cascade impactor. I try very hard nowadays when I'm talking about because we always used to say corona charger, but now talking about corona chargers and corona needles is not very amusing, so we try to avoid using that. So it's a diode unipolar charger. So the charged aerosol then enters into the cascade impactor, where the flow is accelerated in jets, and these jets of air are directed towards the collection surface, and the airflow makes a sharp turn. And the particles that have sufficient inertia, sufficient mass, they cannot make this sharp turn. They come into contact with the collection plate and get collected. And in the next stage, we accelerate the flow a little bit more to gather even smaller particles in the next stage of the cascade impactor. And all of the stages are electrically insulated from one another. So with individual electrometers, we get the continuous current measurement from each size range. And when we have the currents and we know the charging efficiency for different size particles, we can directly calculate particle size distributions and concentrations of particles. Other methods this Dekati E filter, it can be used with a PM2.5 inlet, in which case it's then the reference method for the ISO 16000 part 37 for the PM2.5 measurements. And as said, you are allowed to take a minor side flow after the inlet and before the filter holder, as we do in the E filter. So we have LDSA, or the long deposited surface area, direct measurements, and we can correlate the data to particle number and particle mass. So the instrument is fairly simple and straightforward. We have the 47 millimeter gravimetric PM filter through which we would pull anything between 20 and 100 liters. Of course, in the standard, it's fixed at 2.3 cubic meters per hour for the standard measurement. And then we take a small side flow of 0.5 liters into a chronocharger, followed by a trap and a Faraday cup filter to give us our real-time current reading. There's also some features like a flow sensor, so you can set the E-filter into an automatic mode where the real-time measurement starts when the pump starts to pull the main flow through the gravimetric filter, and when the pump stops, then the measurement stops automatically. So you would basically only, like if you were doing those 3 times of 3 8-hour period samplings, you would only need to program the pump and its start and stop times, and the E-filter would automatically function based on that. And then another instrument is the Dekati electrical particle sensor, which is basically exactly the same as the E-filter, but only does the real-time measurement, so gives you real-time data on LDSA, which can then be correlated into other particle measurements as well. So it of course allows much more easy mobility in the measurements and can be worn, for example, on a belt while you're inside the indoor area. So a couple of examples of what could be done with these instruments. A very comprehensive measurement would be to do sort of center point measurement of size distribution and concentration of the aerosols, and then do, in this case, these would then be reference measurements at different specific places with E-filters that might be the most interesting sources or expected sources to be measured. Another example, we could have one reference measurement of the E-filter collecting a gravimetric filter, and then do, with the same principle, do real-time measurements with stationary units or then moving units, whether it's then on a person or transported otherwise periodically from place to place, to get a more accurate understanding of the time variation and the spatial variation of the PM. So what you could gain from these type of measurements is, when you have the real-time data and you have spatial resolution in the measurements, you could, in this example, you could see what are the areas that have the highest exposure for workers, and timely when it's peaking to lunch hour, for as example, night ventilation, outdoor leakage, how the ventilation system works. And then of course you'd understand what is the representativeness of your long-term samples compared to the real-time data. So this gives you much more thorough understanding than, of course, if you're just doing an average PM2.5 collection over a 24-hour period. So in conclusion, two parts of the standard. We have the part 34 that gives you comprehensive instructions what to take into account in indoor air measurements, and it has a thorough review of the available instrumentation and their operating principles and advantages and disadvantages. And then we have the part 37 that describes the reference method for indoor PM2.5 measurements and has then instructions how to use the supplementary instrumentation to increase the measurement quality and also to increase information, for example, from different sources. So that was my last slide. I want to thank you very much, and I'll wait if there are any questions or comments. And I want to thank you for your participation in this webinar. We have a question asking, is it possible to analyze the chemical composition of the different plates with the LP? Yes, you can do analysis. In this case, what I was discussing here, especially for long-term measurements, we would use the so-called sintered plates that allow us to do very long measurements with the LP. If you want to do analysis, we can use aluminum foils, or we can use polycarbonate foils for the collection of the sample, in which case you can then take samples from each different size range and put them into post-analysis. And this would potentially, of course, be very useful to, for example, confirming what is the indoor air, what are the sources in the indoor air. Yes, that can be done. And nothing in the chat. And of course, if some questions come up later on, you are of course welcome to send those questions to sales at dekati.fi. We have a question. Can LP be used in addition to standard measurement methods to ascertain particle size? Yes, of course. The LP is described in the. It's included in the in this list of methods. It's because they don't want to use brand names in this document, so it's low pressure impactor plus electrical detection. So this is the LP instrument in this list of methods. So yes, it can be used to ascertain the particle size distribution in addition to having the standard method for PM2.5 mass. We have a question regarding the ISO standard numbers for public transport measurements. If it's possible for you to send that question to sales@dekati.fi, I would need to check what are the relevant ISO standard. I don't remember those off the top of my head, but I can definitely look those up for you. And as said, that's really the main thing why it's not basically allowed to use this standard for those measurements is that when there already is an existing standard, if you would use even slightly different method and get different results, then those two standards would be in conflict, and that would be a problem, especially if it would be used for legislative purposes. Okay. I'm gonna wait still a couple of minutes here, but if there are any further questions, as said, you can also send to sales@dekati.fi, and we'd be happy to answer them later on. And if not, I would like to also take the time now to thank you very much for participating, and hopefully you found the webinar useful, and there will be a questionnaire after the webinar, so if you do have the time, please answer that as well.